again, but hopefully it'll be interesting for you to listen to. So there's 5 topics that I've decided to talk about: the priority, issues, and some future directions. And I guess from that perspective, the future directions will be the questions that I would be asking you, because my future directions would obviously be a little bit different to yours. So this sentence, which you can read, I'll talk about from a very famous lady. Her name's Lorena Barber, a key person in any CFD modelling. And she's come up with this new, I guess, paradigm and a way to to ensure that there is quality in our work. And I think just before, in the earlier session, we talked about how can we standardise our modelling and how can we ensure that the things that we're reading are reliable. And so there's this thing called about reproducibility, and how can we create reproducible computational research. And one of the things that she's pushing a lot is to be able to provide your data sets and your code and then your scripts that then generate those figures, and that will allow people to scrutinise our work. And of course that's a great idea to implement, but then there's always a lot of extra workload on those that are publishing that work. And so this, I think, is a priority, and this will lead to higher quality and ensure that a lot of our work will start to become more standardised and then get criticised fairly amongst our own peers. So just a few issues with CFD, and my comments here are based on the finite volume and difference approaches. So depending on your software, then perhaps, and your solvers, perhaps this may not apply to yours, but this is the experience that I've had using the finite volume approach, and in particular the answers package. And so round-off errors are one concern, and typically arise when you've got very high aspect ratios. And to counter that, you would want to be using double precision, but then that comes at a computational cost. Solution errors is the discretization when you're switching from the equations into discrete points. And again, here we recommend that if possible, second order schemes are used. And then the modelling errors. And as I talked about before, is which turbulence model you use and which models are you going to use to represent the physical behaviour. So just an example of the meshing issues we have. So these two are quite bad because you have high aspect ratios and skewness in the corners of that circle. So a high skewness for the circular geometry, and the one below it is bad because it has high change from a very narrow to a large mesh at the interface between the prism and the tetrahedrals. And so you have strategies to change that, and so I think this is the kind of reporting that we would want to work towards when we publish our results, to ensure that the quality is there. And I just talk a little bit about numerical diffusion for those that are unaware, but I think most modelling people do. Now, if we have a look at this, we have a scalar u and v equaling to 1, which means that it's going to be going in the diagonal direction. And if we use a quad mesh, which is structured mesh, then we can see that partition. So if you draw a vertical or horizontal line across that geometry, you should get a step function where it'll start at 1 as you go along the red line and then immediately drop and go to 0. But you see that in a lot of the finite volume models, they will interpolate, and so it's sometimes you don't get that perfect step function that you're after. But more, I guess, worse than that is when you start using tetrahedral meshes, and they suffer a lot with numerical diffusion. So you don't get that perfect step function that you're after, but rather a smearing effect at its interface. And this is another example. So structured mesh deals very well with numerical diffusion, but tetrahedral tends to suffer. So in that respect, we find that tetrahedral cells are very susceptible to numerical diffusion. You may have seen that in your readings as artificial diffusion or false diffusion. It can be overcome with very high order schemes, but a lot of times they aren't available, and when you go to lower order schemes, you, I guess, bring into more stability, but suffers from that diffusion, numerical diffusion. Okay, so I guess the questions we want to ask in these kinds of priorities and issues is, how significant are the effects of skewness, and can we quantify or report our level of skewness? If there's just one bad cell, I think it may not affect the overall flow behavior, but if there's a region of really poor cells, then perhaps it will. So polyhedral cells are relatively new. I think there's promise in the polyhedral cells because they're, I guess, a compromise between, or in the middle between a tetrahedral and a fully structured mesh. And with the commercial software, we have limited discretization schemes that we're after, or that we can use, sorry. Okay, so in terms of our future directions, I'm going to just talk quickly about three things. The mucus and its interactions, fluid structure interactions, and larger samples, and we'll see where that can lead to, larger samples of human airway scans. So we've been working a little bit on mucus modeling and how we can represent the mucus. And this comes from toxicology, so you breathe in particles, you're exposed to particles, you find out where it deposits, and then it penetrates the mucus. And there's already the PBPK modeling approach, the physiology-based pharmacokinetics, but we can also look at how the penetration works through the mucus and then integrate that with the mucociliary clearance. And so this is just something that we decided to work on. When you report your particle deposition, a lot of times you may not be able to see that pattern that is behind the overlapping geometries, particularly at the septum. You can never really see it unless you rotate the 3D model around. And so we thought, well, we have the atlas, the world atlas, the world map that you see. So in the 3D domain, you've got a globe and you can spin around, but how do you represent it in 2D? Well, they just cut it somewhere and then flatten it out. And then we thought, well, we can do that with the nasal cavity as well. So why not take a cut along the floor of the nasal cavity, because that seems to be the most flat part of the geometry, or relatively flat. Open that up. And so we produce this. Let me see if it works. It doesn't work, that's okay. But it was showing how the model will be flattened out into a 2D domain. And we've got a MATLAB interface, the graphical interface that allows you to change the data structures from the CFD into the 2D domain. Okay, so this is what it looks like when you unwrap the model from 3D to 2D. And then you can normalize it from 0 to 1, being that the 0 is the front of the nostril and 1 is the back of the pharynx. So when you look at different patients, maybe a patient has a short nasal cavity, another patient has a larger nasal cavity, then that can be normalized, and you can look at the deposition patterns, the wall shear stress in detail, and have a direct visual comparison. Okay, so we also worked a lot on the rat nasal cavity just because of our toxicology work that we do. So the nasal cavity geometry is a lot more complex, but we show that is still possible to do the unwrapping method. Okay, so when you have that in 2D, then we thought, why not extrapolate down, and then you have a 2D surface, which is also representing the mucus sublayer. And we tried to do this, I guess, novel idea, but physically we're not sure if it's accurate or representative enough. Because if we say that, okay, mucus does move to the back of the throat at, say, 50 microns per second, why not introduce a single vector moving to the pharynx in 2D domain, and then transfer it back into 3D. And so we have some video imaging of dye being injected into the mucus, and some parts are validated okay and looking all right. We're still at preliminary stages of that. So the mucus penetration is something that is a future focus that I think is important. Another one is FSI. FSI is quite challenging. Over three years, and with a project with another student, we had a lot of trouble trying to implement it into the nasal cavity, but we looked at a simple geometry which allowed better convergence and stability, and we showed that yes, the Venturi effect and sucking down of the geometry based on the flow rate and the flexibility of the material there can lead to different airway collapses. I think it can move forward in this respect, but currently the code is not sufficient enough to provide significant stability. So that was done in 2011. We haven't revisited it, so I'm not sure its capability in 2018. Okay, so this is the last topic before I ask you what you think is the future priorities. Now, if we were to get large samples, because in our engineering community, there's certain groups around the globe, and one group may have 20 models, another group has 10, another group may have 50, another group have 30. How can we combine these geometries and share these geometries and work towards a single model? So Carleton University have one, and this is a snapshot from their website, from their website. But you see the model is truncated at the pharynx, and this is a standardized geometry or a combination of geometries over 30 different geometries collected. But you need to email the author to get the geometries. I've made 2 models available online. You don't need to email me, you can just download it. And then if we create this, if we can combine our models, perhaps we can have one SCONA model to rule all other models. And we can call that the SCONA model. So that could be something that we can look forward to in the future. Okay, so that was all I had to say.